Thermodynamics Part 6. Comparison of the slopes of an isothermal and adiabatic process. So first, the isothermal process, we have to use the isothermal equation, that is PV is equal to constant so just to see how to find the slopes of the isothermal curve. So P dV, we are differentiating on both sides, partial differentiation V dP is equal to 0. Which curve we are talking about? PV curve. PV curve. PV curve. And if the curve is the slope, we are going to find out. So definitely we are going to find out the dP by dV. So P dV is equal to minus V dP. Or better to take this thing here, V dP is equal to minus P dV. Same thing, because we are going to find the dP by dV. This taken here is equal to minus P by V. That is, your dP by dV is the slope for isothermal curve. We got minus P by V. Ticket number 1. dP by dV. That is the slope of the isothermal curve. P by V. So similarly, in case of the adiabatic, we are going to use the adiabatic equation PV to the power gamma is equal to constant. Again, partially differentiate. P differentiation of this V to the power gamma is gamma V to the power gamma minus 1 into dV plus V to the power gamma as it is, and dP is equal to 0. Constant ka differentiation 0. Right? Now this is a, so V to the power gamma dP is equal to, इसको यहीं रखते हैं and take this all here, minus P gamma V to the power gamma minus 1 dV. Now dP, this dV we are taking it here, dP by dV to find the slope, that is the slope. So minus P gamma V to the power gamma minus 1 by V to the power gamma. This taken here. So ultimately dP by dV is equal to minus gamma P V to the power gamma, take it up, so it will be the so here V to the power gamma minus 1 into V to the power minus gamma. This comes up, and then this, now base is same, so minus gamma P V to the power gamma minus 1 minus gamma. That gamma plus minus cancel, minus gamma P V to the power minus 1. That is minus gamma P by V. So that is your dP by dV. That is for adiabatic. This is the slope of adiabatic. Now you have to compare this and this, isothermal and adiabatic. If you are seeing properly, here the only minus P by V, here minus gamma into P by V. Obviously this magnitude of this quantity is more. So this curve or the slope is more for adiabatic than the isothermal. So slope for adiabatic is greater than slope for isothermal. Now, how we are going to draw the graph, PV graph? This P axis and the V axis. In case of the isothermal and the adiabatic, if this is the isothermal, then this is whatever the slope is there. You have to remember. And this is your adiabatic. Just to see the more slope is there. This is your adiabatic, this is your isothermal. Expansion. This is for expansion. Here the slope is more. Slope is more. Here slope is less. So for adiabatic, more slope. For isothermal, less slope. Now for compression, that was the expansion. This is for compression. How we are going to draw the slope? Slope is like that. This is your more slope and less slope. More for adiabatic and less for isothermal. जिसका स्लोप ज़्यादा है दैट इज एडियाबेटिक, जिसका स्लोप कम है दैट इज द आइसोथर्मल. नाउ हाउ टू फाइंड द अमाउंट ऑफ वर्क डन? टू फाइंड द एरिया अंडर द कर्व. जैसे फॉर एग्जांपल इन केस ऑफ कंप्रेशन, सो डेफिनेटली एरिया अंडर आइसोथर्मल इज लेस देन द एरिया अंडर एडियाबेटिक. सो मोर वर्क फॉर द एडियाबेटिक केस, लेस वर्क फॉर द आइसोथर्मल केस. वर्क हम लोग कैसे निकालते हैं? Work from the graph, the area under the graph, area under the PV graph, PV diagram. जिसका एरिया ज़्यादा है, यहाँ पर देखिए एरिया जो एडियाबेटिक है उसके अंदर का एरिया ज़्यादा है, होल. वही एडियाबेटिक के अंदर का एरिया कम. Right? So that is the way how to find the area, the work done from the graph. Now, reversible and irreversible process. Reversible process. A process is said to be reversible when the various stages of an operation to which it is subjected can be traversed back in the opposite direction in such a way that the substance passes through exactly the same conditions at every step in the reverse process. It occurs very slowly. Means the initial condition is not reached. For example, compression of spring, melting of ice into water, and freezing of water into ice. Like for example, here I have taken ice. Now I am providing heat. Then it will convert into the water. I am providing it heat plus Q amount of heat I have provided. Then it will convert into water. And if I am going to take out minus Q amount of heat, if it is convert into ice, that occurs. That means it is a reversible process. जितना अमाउंट हम हीट इसको दिए ये बन गया, मान लो Q अमाउंट हम हीट दिए ये बन गया आइस, बन गया वाटर. वाटर से अगर हम वही Q अमाउंट ऑफ हीट को माइनस कर लिए, एक्सट्रैक्ट कर लिए, अगर वो आइस बन गया, दैट इज योर रिवर्सिबल प्रोसेस. वेरी गुड एग्जाम्पल ऑफ द reversible process. Irreversible process. A system in which the system cannot be retraced to its original state is called irreversible process. Most of the processes are irreversible, like the heat generation during the current flowing through the wire or the resistor in case of bulb, etc., or the diffusion of the gases. That is a good example of the irreversible process. जो हीट जनरेट हुआ, एक बल्ब है जो हीट जनरेट हुआ, उससे हम लोग वापस नहीं ले सकते हैं हीट को लेके फिर वो ओरिजिनल कंडीशन में नहीं ला सकते हैं. दैट इज द इरिवर्सिबल प्रोसेस. Limitation of the first law of thermodynamics, that is dq is equal to du plus dw, that is the first law. What are the limitations? Number one, it does not tell us about the direction of transfer of heat. ये हीट का जो ट्रांसफ़र होता है किधर से किधर, किस ऑब्जेक्ट से किस ऑब्जेक्ट, इसके बारे में फर्स्ट लॉ से हमको नहीं मिला. नंबर टू, इट डज नॉट टेल अस हाउ मच of the given quantity of heat is converted into work. Given quantity of heat, how much of the heat is converting into the work, that is not clarified. कितना heat work में convert हो रहा है, how much amount of heat is converting into the work, that is not given. Number three, it does not tell us about the conditions under which heat is converted into work. इसके बारे में क्या कंडीशन होना चाहिए कि हीट को वर्क में कन्वर्ट करने का. So after the clarifying, then the scientists have thought these are the limitations. Then come on to the second law of thermodynamics. Second law of thermodynamics, and it is given. Second law is given by two scientists after the different experimental fact, different activities. Two scientists, Kelvin and Clausius. Kelvin has given a statement. Kelvin's statement: it is impossible to get the continuous supply of work by cooling a body at a temperature lower than that of the coldest of its surroundings. So that is the Kelvin's statement. It is impossible to get the continuous supply of work by cooling a body at a temperature lower than that of the coldest of its surrounding. However, the best one is that of Clausius. Clausius' statement: it is impossible for a self-acting machine unaided by any external agency to transfer heat from one body at lower temperature to another body at higher temperature. मीन्स इस स्टेटमेंट से क्या है, इसका मीनिंग हुआ, जो सिंक होता है, सिंक माने कोल्ड ऑब्जेक्ट, यहाँ पर हॉट ऑब्जेक्ट, सिंक से हीट को एक्सट्रैक्ट करके हॉट में देना ये संभव नहीं है unless and until some external work is being done on this. This occurs in the refrigerator. तो सिंक मीन्स कोल्ड ऑब्जेक्ट. कोल्ड ऑब्जेक्ट से हीट को एक्सट्रैक्ट करके हॉट ऑब्जेक्ट में देना, इट इज़ नॉट पॉसिबल naturally unless and until it should be aided by external agency. Some extra, that is a heat engine. However, this year it is discarded, deleted portion. In case of a heat engine, what happens? The working substance, this is WS means working substance, the hot object and the surrounding or the sink, cold object. From the hot object, the working substance is going to extract the heat, taken the heat, and some part is sent to the cold object, sink, and the rest part to the work done. So if the Q1 amount of heat is taken by this working substance, then say the Q2 is sent to the sink, the amount of heat converted into work is your Q1 minus Q2. Q1 minus Q2. That is your amount of heat, amount of work done. That is like W is equal to Q1 minus Q2. That is in case that occurs in the heat engine. And the reverse, that is your, in case of the refrigerator, the reverse of the heat engine is your refrigerator. In this refrigerator, what happens? Thus, from the sink, that is a cold object, the heat is to be extracted with the help of the work done. Without work done, it is not possible. The second law also states that without that work done or external agency, it is not possible to extract heat from the cold object and send to the hot object. So that external work done is required to take the heat from the sink and send it to the hot object. So in case of refrigerator, what happens? That compressor is doing this work of the work. Compressor doing the work on the working substance over there. That is a freon or something is there, ammonia gas or something. So they are taking out or extracting the heat from the object or the eatable item and send it to the hot object. And remember, that occurs in case of refrigerator. If you have opened the fridge, the temperature of the room increases. That's important, because inside the temperature is low, outside the temperature is more. So temperature or the heat is extracting from the object inside and send it to the outside. Okay, thank you.